So, good afternoon, everybody. It's very nice to see all of you here, and I'm very, very happy to be here to introduce the new academic year of the Brussels Institute of Advanced Studies. So, as you can see from the slide, the theme of this year will be on robotics, and in particular the question about the fact that robotics can be both an enabler or a disabler for what concerns sustainability. It's a huge opportunity and a huge risk at the very same time. But we were speaking first about the Brussels Institute of Advanced Studies, and where we left last time was here. So last year and the year before, there was a previous theme concerning the past, present, and future of food, climate, and sustainability. So you see there is one theme that continues, that is the one of sustainability. We started in the first 2 years of the Brussels Institute of Advanced Studies on food, climate, and sustainability. We are now moving toward how technology, and in particular robotics, impacts these things. So a few words on previous years. There were 2 seasons with a large number of fellows and participants. And in particular, I would like to take this first moment to thank the former program directors. In particular, in the previous years, there was Professor Christian Hermans and Professor Fritz Heinrich, who were the directors of the program of this institute, and there were also 2 co-directors, Nel de Mouliner and Professor David Cannella. And also we had 2 former administrative managers that did a lot to establish this Brussels Institute of Advanced Studies. And as a first thing that I would like to do in this, before starting speaking about the new program, it's to ask to the 2 directors of the Brussels Institute of Advanced Studies to say a few words, and after that I will ask them to help me with a small ceremony to acknowledge some of the people that are present for their work in the previous years. Please, the directors.
Thank you very much, Emanuele, and my colleague Serge Jaumain. I'm Frank Deconinck, the BrIAS VUB director, if I may say, and Serge is the BrIAS ULB director. I just prepared a few slides. You have already said a couple. I don't know whether it's possible to switch to this computer, and I hope this will work. Yes, wonderful. So first of all, on behalf of Serge and myself and BrIAS, welcome. Happy New Year also, and welcome not only to you here, but also to all the attendants which are following us remote. I hope because I'm a Macintosh user, so this is just a few words of history, very short. But BrIAS, the idea of BrIAS and the decision to found BrIAS was made in 2018 at the request of 2 former rectors. You see Caroline Powels, who was rector of VUB, who unfortunately, very sad, passed away a few years ago, and Yvon Angler. And they had the initiative to create BrIAS and to ask us both to create BrIAS as an interdisciplinary incubator of ideas. So BrIAS is not project-based. There is no project with milestones, etc. It's a brainstorming organization in which people from different disciplines work together on a broad subject. In total freedom, the people working together are supposed to be high-level experts in their field, which again is extremely wide. And the hope is that through discussions, there will be an emulation, there will be new ideas that come up, and that eventually will give rise to projects and collaborations. So this is the basis of the Institute for Advanced Studies. The first theme, as it was already mentioned, was on sustainable food. And we have Christian Hermans, who is sitting there in the back, who was one of the program directors from the ULB side, mainly Fritz Heinrich, Christian is a biotechnologist and plant genetics, is this approximately correct? Yeah, and bioengineer, and Fritz is more archaeobotany. So you see totally different fields, and we had a historian, people from different disciplines. This is essential in the philosophy of BrIAS. And they, for 2 years, they had fellows coming, and you've shown the pictures of the fellows working on the past, present, and future of food, climate, and sustainability. As Emanuele said, this year's theme is Sustainable Robotics. I can go very fast on this. What is special for this year is the fellows today are in a hotel in town, and we have our meeting here. But from, say, summer 2024 on, BrIAS will be situated in those renovated military barracks, which are just next to the other campus of VUB and ULB. And for example, here we will have most of the housing. Here we'll have the seminar rooms, etc. I have just a few pictures to show you the actual state. They're being renovated. You see a studio. This will be the co-working area. This will be an ideal setting for people to live together, to work together, to interact, to discuss, etc. So we really look forward to the new setting, which will be available, as I said, probably from May on, and certainly December. Now, I wanted to keep it short. I will keep it short. I did not resist on showing you a robot snowman. And by special request, I also show this, drawing the illustration for the last workshop, normally, of BrIAS in May on agriculture. And apologies to the artists which are in the room for the quality of the images. I wanted to keep it short, and
thank you, Frank. Thank you, Serge. And if I can ask you to stay here, and if I can call the former director of the program, Christian Hermans, and the former administrative manager of BrIAS, because we have a small thought for them that we would like to present to them. So it's a small token of our appreciation for the work that they did in the past.
I wish you all the best in this adventure. last year when it finished, so I had tears because these two men, they gave us freedom to organize such a nice adventure. And I wish you all the best, and to the people at VUB too.
Thank you very much, and we hope to be at to do at least as well as you did in the past, and it's a very challenging task. Okay, so yep. Okay, so a little bit of technical passages. So, as said, we have acknowledged Professor Hermans and Dr. Porco that really did an amazing work in the previous years. And so we can start speaking a little bit about the theme of this year, and I will try to not waste too much of your time because I imagine that you are interested and curious about the actual seminars. So, as said, we were presenting this theme about the fact that robotics can be both enablers or disablers of the development goals. And so the question is why we did that. Well, our starting point was that we can consider, if we look at the present and then the future, as robotics as a paradigm shift in what we consider as a civilization. So the more and more we have a passage from manual labor performed by people to labor performed by machines. And this is pervasive, and in certain fields it already happened some decades ago. If you go now in a nowadays automized factory, you realize that there are very few people and a lot of robots, and this will be more and more in other fields. So, of course, this raises hopes and also raises concerns. Hopes, it's easy to think that in certain fields, for instance, I think to agriculture, the passage in the last 50, 60 years from manual labor to automized, machinized labor, yes, decreased the number of people working in agriculture, but it also decreased the number of people starving in the world. Simply, we got a much bigger production with much less labor. And so this is one of the cases in which it's easy to see that there is a case for more automation as being a basis for achieving goals. On the other hand, it also raises concerns. Of course, the classical one, it's the one that I mentioned before, loss of jobs, but also ethical concerns about who makes choices and who performs certain actions. So really, what we think is that since robots can be an enabler or a disabler, the reflection must start from here. And of course, we are more in favor of the green part rather than the red part. And so the reflection must start from academia, so from research, but also from the usage in the industry, and cannot be just relied to the technical part, but must also concern how we see it from a socio-economical viewpoint. So this is the idea that was behind this series of reflection that brought to this theme. And we really think that what we must do is to raise awareness and to foster interdisciplinary research and development in such a way, because this is our goal, to push for a robotics for the common good. A preliminary work in this sense, and this is an image grabbed from a paper of one of my co-directors and the other director, Bram van der Boer and Karl Mork, that are here. It's about analyzing how robots can be enabler for the 17 Sustainable Development Goals developed by the United Nations. And for each of these 17 goals, we can find potential benefits, but also potential threat. And this is the starting point of our theme of this year. Now, of course, we We will touch a little bit everything, but we have also defined some themes that are somehow some of the guidelines of the general subject on which we will focus a little bit more during this event. And in particular, we will have 4 main themes and everything that is around. The first will be robotics and agri-food. This is also to create a bridge with respect to the previous subject. Then we will have a second subject concerning sustainable robotic technologies, so how the robot itself can be made sustainable. And then a third application that is robotics for health and well-being. Now, you will see the fourth one, and this was also one of the themes on which we discussed the most before putting it in the equation, that is robotics in time of war and in time of peace. And the idea is that it's a fact that if we just look at the newspaper, there is more and more robotics on the battlefield. And this is, of course, something that on which we want to raise awareness on which are the facts that are happening and which are also the ethical and legal aspects linked to that. And at the very same time also speaking about the peace in the sense that robotics developed in the field of military, on the one hand, can be maybe not a nice thing, maybe an horrible thing on a battlefield, but at the very same time are also the same that can make the world a nicer place by, for instance, doing demining work or diminishing threat due to all remnant of wars. So, a little bit something about these various subjects. So here some image from some projects we developed in the past concerning robotics in agriculture. This is something that is slowly arriving there, and it has, we think, there is a lot to do still. There is a lot to be encouraged, and there are also some aspects sometimes to be aware of. A second subject, and here some other video concerning what we mean by sustainable robotics technology. Here there is some work of my colleague Bram van der Borg from the VUB concerning robots that can self-heal and so that are can inherently last longer and survive injuries, bad treatments, and so at the end be more sustainable in terms of usage. A third example that I want to show, it's on the third theme, well, robotics for health and well-being. Here there is some videos of some prosthesis. Robotics has tons of application for prosthesis, for rehabilitation, for surgery, and there are even more applications that are being studied as we speak. And we believe this is another theme that is quite important to treat in our BrIAS season. Fourth subject, as we said, war and peace and robotics. Now, the previous videos and images were all work done either in this lab or in the labs at VUB. This is the only image of the presentation that comes from the internet because we don't work on this kind of applications. But we believe that it's important to raise awareness and to understand that there is a complex debate concerning the use of robotics in war. And that's a debate that cannot be left only to professionals of politics. It's a debate in which academia must have a role, must bring its position, its viewpoint, and actually must also be the place where different opinions meet and where we can have then a constructive dialogue on the subject. Now, I must say the title is War and Peace and Robotics, and I didn't want to finish this presentation on, let's say, a grim note. So I can also show you how robotics can be used at peace, and this is actually a video that comes from the website of a company involved in the Belgian marine demining program. And this is basically the new generation of Mindhunter of the Belgian Navy. And the idea is to use a lot of robotics in such a way to do the demining with as least as possible people involved with underwater mines that could explode, that could be not the nicest thing on Earth. And the idea is to demining in a faster way and in a safe way. So you can see when I was saying there are positive aspects, there are negative aspects, what I meant by that. Okay, so this is an overview of the theme. Now let's speak a little bit about organization. So first of all, the people involved. You had already the possibility to meet the two BrIAS directors, Professor Van Deconinck and Professor Jaumain. And we also have a new BrIAS manager, that is Dr. Garone. Then finally, we also have, oh, there is some problem in the slides. We have the new program directors, that is me and Professor van der Boer, and two program co-directors, Dr. Mork and Dr. Jacobs. And we also have a special advisor from the Royal Military Academy, that is Professor Gert de Kuber. Besides that, we have the involvement of many professors and even more postdoctoral researchers and PhDs, many of which are in this room today. And I also want to mention that these activities will be carried out with FARI, that is the Center for Artificial Intelligence for the Common Good. It is another joint activity between ULB and VUB, and the collaboration from the Royal Military Academy. So we have, this year we will have 16 senior fellows from 12 different countries and 9 junior fellows, most of which coming from ULB, VUB, and universities not too far geographically from here. And the program will be more or less like this, so there will be every Thursday, exactly like today, a series of 2 or 3 talks with fellows. Usually 1 week it will be here in this lab, the other week will be at the VUB in the experience, in the AI Experience Center. And we are also organizing 4 major events in some specific dates. In particular, we will have 2 days on robotics in agriculture on the 15th and 16th of February, 1 day on sustainable robotic technology on the 29th of March, another day on human-robot collaboration on the 26th of April, and finally a last forum on war and peace and robotics on the 2nd and 3rd of May. So all the events will be streamed like this one, seemingly. And for the rest, what I wish you is to have a very nice season of this Sustainable Robotics Fellowship of this year. And of course, what is important to say is that most of the work, it's not the seminars, it's not the workshop we will have together and the public forum, but the really important part of the work is to create connections, to speak outside of these events. These events must be point where we start the conversation or where we understand what the others are doing to then collaborate more. So with this, I conclude here. I hope I have not made you too much tired with too much words, and finally I can leave the stage to our next speaker. Someone told me that I forgot something very, very important. That is, this year we also have a news. That is, we also have the collaboration with Home, which I'm full of guilt. I forgot to put in the slides. And we also have resident artists that will join the fellowship. And it's a pleasure to have you with us, and we can't wait to interact with you too. So at this point, I can finally leave the stage to our first senior fellow, visiting us. So I can, in the well, maybe you want to switch. Thank you. So it is really my pleasure to introduce him, also because we know since a very long time. It's Professor Francesco Lamonaca from the University of Calabria in Italy. So he is an expert in measurement systems and has tons of appointments in the various measurement associations. So I will not stay here to say all his CV because it's quite long. I was very pleased to invite him. He's not, strictly speaking, a roboticist, but that's exactly the kind of message that we want to give. We don't want to speak only about robotics for the roboticist, but also try to widen a little bit the horizon to have vision from different viewpoints. And in particular, as said, Professor Lamonaca is an expert in measurements, and today we will speak to us about measurements for sustainable robotics and automation. So I leave you the stage.
Thank you, Emanuele. Thank you all. Thank you, the directors, for selecting me as fellows of BrIAS. It's a big honor for me. As Emanuele told, I'm expert in measurements. So in these slides, I'm trying to give you an overview of what measurements means for robotics and automations, and what robotics and automation means for measurements. And this is the outline of this presentation. Just a few words about myself. Measurement, robotics, and automation, a successful synergy. I will introduce my laboratory for the elaboration of measurement information, LAME Domenico Grimaldi, and some case studies that deals with our laboratory. Characterization of shape alloy, structural health monitoring, monitoring of cultural heritage, time synchronization. This is me. I'm Associate Professor of Electrical and Electronic Measurements at the Department of Computer Engineering, Modeling, Electronics and Systems at University of Calabria. I have achieved the National Scientific Qualification as full professor in electronic measurements in 2020. I'm the director of the International Scientific Journal ACTE-MECO, editor-in-chief, the Diamond Open Access Journal of IMECO, that is the International Measurement Confederation. I'm senior member IEEE and belong to the Instrumentation Measurement Society. I'm vice president of Commission A, Measurements for Electromagnetic Fields of URSI, International Union of Radio Science, Italy section, and I was president for many years. I'm fellow of BrIAS, thank you. I'm president of the Commission for the Management of the Informative System of the Italian Group of Electric and Electronic Measurement, GME. I'm president of the MECO Commission for Publications, and I'm associated with the National Research Council, CNR Nanotech. And I'm the scientific coordinator of the research unit in electronic measurements at the University of Calabria, and serves as general chair of the IEEE International Workshop on Metrology for Living Environment. And I'm responsible of several projects, and for many years I am in the ranking of Elsevier and Stanford among the top 2% of scientists with highest impact. So thank to them for this. Sorry. Measurement and robotics and automation, a successful synergy. Measurement science aims to retrieve objective information about properties of physical phenomena and magnitude. But this information is not an absolute truth, but it is affected by uncertainty. Please note that this uncertainty does not deal with errors. You know, when you study physics, there are systematic errors, accidental errors. Uncertainty comes from 5 main factors that are the knowledge about the measurement, the standard of the measurement unit. I mean, the unit that we have is not the reference one, and the unit propagates through us, and when it propagates, it comes with an uncertainty, the operator, the instrument, the measurement method that we select. So we need to deal with this uncertainty, and we deal it with the probabilistic approach. This is into the GAM. The GAM is the guideline to the expression of measurement uncertainty. And we need to quantify this uncertainty. This to compare measurements, This to make informed choice, this to set up adequate countermeasures by predicting the effects of decision made on knowledge that cannot be absolute. Automation has permitted the development of automatic measurement system that evolved in distributed measurement system. This has allowed unprecedented possibilities in the monitoring of phenomena from the nanoscale up to a planetary and space scale. Smaller automatic measurement systems are based on nanosensors from the monitoring of chemical, mechanical, biological, or optical quantities. Some of them are implantable. The bigger one is the satellite systems for the monitoring of Earth physical quantities, but also to share a common sense of time. Robotics has permitted the development of advanced automatic measurement systems for inline inspections. Unmanned systems are mobile measurement platforms able to automatically detect the better conditions to execute the monitoring and to access to dangerous or less accessible sites. Unmanned systems are equipped with sensors, contain all the measurement chain of signal conditioning and processing up to the extraction of measurement information. But what is the open problem for my scientific community? Is the metrological characterization of this new measurement device and system. But, however, this successful synergy, in my opinion, and in the opinion of many colleagues, is the key factor to achieve the end goal. This is the laboratory of elaboration of measurement information, Domenico Grimaldi. There is me, Professor Luca Carni, he's Associate Professor of Electronic Measurements, Professor Marco Ricci, Dr. Stefano Loreti, Rocco Zito, Francesco Felicetti, and the new PhD, Istam Ul Haq. And all us works on measurements, of course, but also on the extraction, the design of non-destructive testing method. These are the last projects that we are going on. Tech4U, you have, I think that you have heard about PNRR. It's the National Plan of Resiliency and Resistance Against COVID, poverty, and so on. And we have won this project, this Tech4U, that have gained 22 million euro, one of the biggest in Italy. Sustainable data-driven manufacturing, Radiomica, an open network for cooperative radiomics and radiogenomics based on artificial intelligence. Oceanos, monitoring crops and coastal marine areas, new generator satellite technologies. Extendable, and the network of extended reality-enabled laboratories for remote practical training. And the last one is the PRIN, the Italian factor of magnetic modeling and spintronics. About Extendable, it's not only a network of laboratory, but this is the way in order to open the door to students that maybe are far away, cannot have the opportunity to reach the university, to make in a virtual environment real experiments, so to access in laboratory. And this is the way to fulfill difference, for example, also gender differences, because often women are less, have not the opportunity to attend laboratories due to time constraints, due to family, due to child, and so on. This is about the characterization. I will start with a case study that is characterization of shape memory alloys wire resistivity. Why? First of all, maybe it must be on. What is nitinol? Why shape memory alloys? Shape memory alloys are unique class of alloys that have the ability to remember their shape. I mean that they return to that shape even after being bent. At low temperature, a shape memory alloy can be seemingly plastically deformed, but this plastic strain can be recovered by increasing the temperature. We have used the nitinol, we have studied the nitinol, Nickel Titanium Naval Ordnance Laboratory, from the name of the laboratory in which it was developed in 1959 by William Buller. And Why this? Because since upon returning to the original shape, these materials generate a significant force and are suitable in the use of creation of actuators, such as in the form of wires or spring. The application of these materials range from development of artificial muscles for humanoid androids to the production of surgical stents and even the creation of wheels particularly resistant to deformation installed on rovers used in space mission. But it can also be used, for example, in automotive, because this allows to change the shapes of part of the car, part of the motorcycle without using engines. So, which is the goal? The goal is to use nitinol to realize actuators with self-sensing capabilities. In order to do this, we need to know with high accuracy the relationship between material transformation, resistivity and temperature, different stress conditions. So our proposal is to set up an automatic measurement system to establish the relationship between resistivity and temperature of nitinol wire under various stress levels. And now the measurement problems. This is the case of the measurement of a low valley resistance. Usually for this case, a double bridge Thomson is used. But we cannot do this because in order to heating the wire, the most accurate way is to use the Joule effect. I mean, we use current to heating it. And in this case, the Thomson bridge cannot be used. So we selected to use the voltammeter techniques. And in this case, although from a theoretical point of view, put the voltmeter before or after the ammeter is the same things, due to the fact that the internal resistance of ammeter and voltmeter is not zero or infinite, as the theory wants, we need to make a proper selection. And of course, we used the voltmeter after the ammeter because this allows us to have the highest accuracy. Moreover, we are able, of course, according to the guide to expression of measurement uncertainty, to evaluate the internal, we know which is the internal resistance of the voltmeter, we correct it, and then we can evaluate the measurement uncertainty. But there are other problems that we need to deal with. For example, the synchronization of measurement procedure and the check of the wire temperature before and after the measurement procedure, because we need to synchronize the acquisition of voltage and ampere to evaluate the resistance and then the resistivity. Synchronization, however, introduces a delay. We have uncertainty on synchronization. And in order to assess that this uncertainty is negligible, produce a negligible effect on what we want to measure, we need to evaluate that the measurand does not change during this time. Another problem is that the resistivity deals with the length of the wire that we want to measure. In this case, the length changes during the measurements, because this is typical of all materials, but especially for the nitinol wire. So our idea is to fix the length of the probe and left the wire to lift over the probes. And we know the distance among probes, and so the length with an accuracy of 0.05 millimeters. But more important things, this uncertainty becomes a constant in our measurement. In this way, the uncertainty with whom we know the resistance is the same uncertainty with we know the resistivity. This is a block scheme of the automatic measurement system we have proposed, and this is its realization. We have used the thermography to measure the wire temperature for two reasons. First, use probes connected to the wire can change its behavior. Second, we can monitor that there is no difference of temperature in the wire, due, for example, for the fact that we use it in a vertical way. So the heating from the bottom can heat up more the ones up. But we have to calibrate, we have pointed out a system to calibrate the temperature measurement, because when you use thermography, you can evaluate a differential temperature in the order of 0.001 Celsius degree. But the offset that you measure can be around 1-2 Celsius degree. So the uncertainty as offset is huge. So this is the block scheme of the automatic measurement system. Essentially, we are able to do repetitive measurements during the cooling and the heating phase of the test of the wire. These are the measurement instruments that we have used with their uncertainty and metrological characterization. These are some experimental results. We have conducted 5 tests using different load on the wire. In each test, 10 consecutive measurement cycles are performed, during which 108 measurements were taken during the heating and equal number during the cooling. And we see an hysteresis cycles of resistance as shown in the figure that is compatible with other research in literature. And of course, the same shape is, the same results are for resistivity, because it's, the length is just a proportional factor. And we have noticed that by applying a weight, so mechanical stress, these curves change. So the transformation temperatures are in direct proportion to the applied stress, and there is a strong dependence of resistivity not only on temperature but also on the applied mechanical load. And these results are promising to use the nitinol not only as actuators but also as sensors. Of course, as it's traditional in measurements, we use interpolation to achieve a global view of the behavior of these materials, also with weight that we have not tested. These are some suggested readings, and we have just received a Bronze Best Paper Application Awards at the E4 SDG 2023 conference, international conference. As concerning with structural health monitoring, in these slides I have tried to summarize some years of research. In particular, what we are proposing is a device that can be installed by robots, especially drones, for example, new generation of drones. What is a crack? A crack is a rupture inside the building material occurring due to stress, aging, and other damaging factors. It can be visible or hidden. And when a crack occurs, energy is released in terms of an ultrasonic wave, also known as acoustic emission. So we can use sensors as a piezoelectric sensor to detect it, which is the advantages with other traditional techniques, for example, ultrasound techniques, that this approach does not need actuators, so we can save energy. And this is fundamental for an IoT approach, for example. Conventional crack detection methods rely on manual inspection, which are time-consuming, expensive, and do not offer real-time data. Accuracy and reliability of these inspections are dependent on the expertise of the inspector. Numerous disasters caused by unnoticed cracks in structures underline the need for a cost-effective real-time crack detection system. For example, Silver Bridge collapse, Mississippi River Bridge, Genoa Bridge, and the last of these, 2023, New York City car park collapse. So our proposal is a wireless crack detection system based on IoT and acoustic emission. This is the simplified block scheme. We use the GPS and the exchange of messages in the case these systems are put inside the buildings in order to synchronize them. And they are able to acquire the signal, process the signal, understand if the signal is significant or not, and send an alarm to a central station to be processed. What we have done, I skip some slides for technical slides. We used the R15 alpha sensor. It's a resonant system, a resonant sensor at 150 kilohertz, because in this way we can increase the sensitivity of the sensor. And from this we have extract information with the previous tests that are destructive tests in order to understand, to distinguish between important signal, acoustic emission signal, from other acoustic emission signal. It's like with an earthquake. We have the first shake that is the most important, the ones with full energy, that may be preceded or followed by other shake that are less important. So we have used the same techniques that is used for earthquake. So this is how it is built, our choose. It is based on a commercial microprocessor that offer some advantages in order to elaborate the signal without losing measurement information. So we use the GPS, and we can create signal with microsecond resolution. So this resolution, time resolution, is good for our application, I mean the detection of the crack. This is the block scheme of the hardware that we realized, and this is the algorithm function. Essentially, the story that I said you before. When we receive a signal, we detect that this signal is important, we send a message with the timestamp at the message to the central unit. This threshold values, this system is small, has less elaboration capacity, so we have used the techniques of threshold. These two threshold for the amplitude 0.47 volt and for the RMS 0.4 volt comes from our previous research. Why two threshold? Because in order to save energy, we use a watchdog. So we start the acquisition of the signal if in the case the watchdog reveal a signal that is bigger than 0.47 volt. So we need to test our hardware. Now the problem is that this kind of tests are destructive, and we need to compare the results that achieved with by our hardware with the ones that we achieve with the most expensive measurement systems. So we have chosen to use the previous signals that we have stored and put these as input to our system. In this slide you can see the load curve. I mean, when you compress the specimen is a concrete cubic 15 centimeter according to the norm. You achieve this curve, this load curve. So this is essentially the response of the cube to the compression. And from a structural point of view, the most important part are these and these. The first and the second flex. The second flex, when we reach this point, it means that the material, the building material is very, very stressed and is ready for collapse. And as you can see, with our hardware, we can achieve, we can monitoring this, and we can select, we detect this signal exactly in the first and into the second flex. So this hardware is suitable for this purpose. So essentially with this last research, we have condensed all the information coming from these systems to these systems. Here are some readings, and from these studies, we have developed together with other colleagues, we have the idea to this IEEE International Workshop on Metrology for Living Environment. The first edition was in Cosenza, in Calabria, at my university. And as the first edition, we had 100 participants in presence and other 50 participants online, and about 90 accepted the work. The second edition was at Polytechnic of Milan. Now the third edition will be in Kania, Crete. So if you are interested in these topics, or you are working these topics, you are welcome. I'm serving as general chair for all these editions. Second case of study is the monitoring of cultural heritage. This is the one supported by the PNRR project Tech4U. I bring to your attention just one case. The case is Casignana Villa. Casignana Villa is an ancient Roman villa about 2000 years before Christ. It's beautiful. we have a lot of mosaics that are perfectly saved, and you can see also the heating system of the villa. What they did, these are 10 acres, the extension of this villa, but they have uncovered just 0.5 acres, so it's something that is completely a discovery. What they did to save the mosaic from the weather condition is to build a roof. But the problem is this. If the temperature difference between the mosaic and the roof overcomes 6 Celsius degree, the tiles of the mosaic start to break. So what they asked us is to develop a monitoring system to detect the temperature difference between the roof and the mosaic. Another problem that is also a measurement problem is the impact, the visible impact of the measurement system. I mean, people that comes to the mosaic to visit the villa have to put attention on mosaic and not on the device that we install. So what we have designed is this distributed measurement system, of course, and a single node of the measurement system is made by 2 thermal cameras, 2 lepton. These are big like a pencil, a rubber of pencil. And we have added the temperature sensor, the absolute temperature sensor. Why? Because as said before, okay, this is the final goal that we want to achieve. So all this node can communicate to a gateway, then on internet, and then to the research center, to the control room, and so on. This is the hardware that we have pointed out. This is the size of the lepton. But the problem here is that the offset, the uncertainty on the offset value of the thermal image that we achieve is plus or minus 5 degrees. Since we measure a difference, it means that the uncertainty on the difference that we want to measure is 10 degrees. It means that the uncertainty is bigger than the value of the measurement that we want to measure, that we want to evaluate. So we propose an online calibration system based on the temperature sensor, and we have reduced this uncertainty from plus or minus 10 degrees to plus or minus 1 degrees. So this is acceptable, but we are working to reduce it through a series of calibration. Finally, we achieve another advantages by using thermography, and it is the impact, of course, because it's like with one node, it's like to put 600,000 sensors on the floor, and the fact that we can detect water. And the water for cultural heritage is a huge problem because water brings life, and life means biological attack. So the main idea is to detect water, and then we can send a drone equipped with ultraviolet light and then acquire invisible light in order to detect if there is life on the mosaic, and then to program intervention to clean it. Of course, we have another big advantage with these techniques is the online monitoring and the constant monitoring means to timely act. Timely act means to preserve our cultural heritage, but also to reduce the chemicals that we need to clean it. Some readings. And we have just started a collaboration together with the group of urbanistic group and geomatic group of my university. I have these drones that is multispectra, DJI Phantom multispectra. They have the ones with the LiDAR in order to create a database where we can use the artificial intelligence to extract information about the damage of the buildings without in a completely non-invasive way. So some advantages. Finally, I bring to your attention the problem of clock synchronization. Clock synchronization, why? Because in distributed measurement system and often in robotics, we need to act with several agents. several measurement instruments, for example, because we want to have a measurement that is huge. We need to monitoring it. Or we need to perform indirect measurements. So in this case, indirect measurements, as into the first case that I bring to your attention, is we assume that we are doing synchronized measurement. In this case, the uncertainty on synchronization is reflected into uncertainty with whom we know the measurand. If in standard synchronization distributed measurement system, we can use GPS, we can use the precision time protocol IEEE 1588, we can use trigger signal that propagates and allow us a delay that we can know this delay. It's about, it depends on the length of the cable, essentially. In the case we use wireless sensor network, and this wireless sensor network can include mobile nodes, for example, some drones, UAV, and so on, these techniques cannot be used, and often we use message passing techniques. We can monitor in different phenomena, and the accuracy that we want to achieve depends on the dynamics of this phenomena. The problem here is that we have demonstrated, together with Emanuele, when I was visiting a researcher here some years ago, we have demonstrated that, first of all, the synchronization accuracy increases with the number of exchanged synchronization messages. But increasing the number of exchanged messages means to consume a lot of energy. So if you are using a battery-based node, you reduce the lifetime of your measurement system. So, a case is, for example, the monitoring of a bridge, in which, in the case of acoustic emission, this acoustic emission will be heard, will be sensed only by some nodes. So, the main idea with Emanuele was why we need to synchronize all nodes with the same accuracy. We need to synchronize with high accuracy only the nodes that are doing the measurement. So we have proposed to split the nodes in finite fine synchronized subset and coarse synchronized subset. So this will reduce the energetic consumption of the nodes. So the idea is to point out a way, an automatic way, with whom this node can change from quiet to alert, from alert to quiet, and maintain the synchronization accuracy required for the wireless sensor network functioning. For example, if you want to go in a sleep mode and you want to wake up to exchange messages only in this window of time, it means that we need to share the common sense of time. Again, we need to be synchronized. But at this point, this window, the duration of this time window depends on the synchronization accuracy that I choose. The organization of this node must be fast in order to increase the monitoring accuracy, light, due to the limited computational resource of the node, adaptive due to the unpredictable occurring space and time of the phenomena, and decided by each node in autonomous way. Master-slave synchronization algorithms are fails in this case, for example, because the master could not belong to the fine synchronized subset. And moreover, this kind of algorithms need a logical structure. When they lose a logical structure, for example, because a node is missing, they need a time in order to reconstruct this logical structure. Another problem is that the logical structure may be different from the geometrical distance among nodes. So, we have based our research on consensus synchronization algorithms. And in this case, the common sense of the time is established by the interaction among the wireless sensor network nodes to reach the agreement consensus on a common sense of the time. This kind of algorithm are resilient to node failure or reallocation, and the communication among all nodes but what we need is that the communication among all nodes must be granted. This not means that all nodes must communicate with all the other nodes. It just means that the graph must be connected, fully connected. So this, the average time sync algorithm was the basis from where we started. This allows to compensate clock offset and frequency. It is robust to packet loss. The convergence was demonstrated. It was experimentally tested. And to increase the lifetime of the node was proposed the use of a slow frequency clock and reducing the synchronization accuracy. Proposal, so we change the frequency with whom the nodes exchange the messages. In order to guarantee the overall synchronization, we use this expedient. I mean that the synchronization period of the defined synchronization subset node must be an integer that is multiple of the ones of the coarse node. So this is the block scheme of the algorithm that runs into this node. We did real experiments by using Telos B and XM1000 nodes. So we have a clock radio, clock servo, clock event detector, and what these are in red, there are the exchanged information. And another problem that we have deals with is the fact that multiple events can occur. In this case, the problem could be to have two different sense of time in the network. So we have developed a software that allows the self-creation of a bridge. So it's like a virtual trigger for some nodes that create a bridge, a communication bridge between these two subsets. In this case, we achieve a unique sense of time. And these are the experimental tests executed on 49 nodes. Further consensus approach advantages. I cannot show you all the research, but we have worked on the prediction of the final accuracy that you can achieve on the basis of the communication delay. And this is a paper that we have published together with Emanuele on Automatica. And we have seen that mobile nodes not only do not create problem on the convergence of the network, but also can be used to speed up the convergence time and reduce the uncertainty, the time synchronization uncertainty. These are some readings. And in this slide, I've added it just to show that we are working. I've started with biomedicine. In particular, in this case, what is the problem? We worked on a new kind of flow cytometer that is able to detect also the image, because traditional flow cytometers just detect the shape and some geometrical properties of the cell, the counting of the automatic counting of the cell. In this case, it is able to take pictures of the cell. And why we are interested in the picture? Because we used this device. It was developed together with the National Istituto Pascale Tumori of Naples. Lymphocyte, human lymphocytes are very sensitive to carcinogenic agents. So we can see this because into the mitosis phase, part of the genetic materials, instead to be doubled and just contained the two nucleus of the two daughter cells, comes as micronucleus. So if you are able to count the micronucleus to quantify their size, their surface, then you know the probability, the strength of the cancerogenic agents on the human body. The problem that we had and give the start for the new project Radiomica is this. Okay, we can apply artificial intelligence, we can apply several vision techniques, several vision methods, but are we sure that the image that we are processing has a good quality? So we need to standardize the image quality. And in our research, we have developed several indexes, measurement index, to evaluate the alterations. For example, in this case, there is out of focus, but there are several kinds of out of focus, for example, blur. But there can be other kind of alteration, maybe overexposure, underexposure, especially in the case of genomics image, radiomics image, can be the motion artifacts. So, all this to say the importance of measurements to give quality to the results that we achieve with other techniques, especially in biomedicine. In conclusions, this task would highlight the synergic efforts of the research in the robotics, automation, and measurement fields. Measurements serve automation and robotics to retrieve objective information from the world, opening new frontiers of their application. At the same time, automation and robotics have opened unthinkable opportunities for measurements such as automatic measurement system, distributed measurement systems that nowadays include mobile measurement nodes, i.e. the robots. If some years ago the aims of automatic measurement system was the reduction of uncertainty by avoiding human operator errors and increasing the number of measurements per unit of time, today is the retrieval of information in place and by point of view inaccessible before, sky, oceans, deep space, and on the other side, inside body and the same materials. So, thank you for your question, your attention, and if you have any questions, I'm here. And these slides even another open topics on which we are starting to work. I mean, can the artificial intelligence can be used in law, so to take decision, also legal decision. And this is a very huge open problems that start working. And these questions comes from layer from judge and so from the legal point of view, legal science. Thank you very much.
Thank you very much, Francesco, for your nice talk. It was nice to see a number of different applications. In particular, you showed us first how measurements can help robotics. In particular, you were showing these very interesting applications where an actuators actually can work also as a sensor if you really know what to look into, which opens quite interesting applications. Then, if I remember well, you showed us two applications, one in crack monitoring and the other in cultural heritage monitoring, where on the other end it's robotics that can give a hand to measurements. Then I must say that with a little bit of emotion, I saw our old papers together. Now it's a research that we did 10 years ago.
Yep.
And that's, I think, it's a very interesting application in which you show us different disciplines, measurement systems, control systems, telecommunication, and in the last step also robotics must work together to reach solution, which I believe is a very interesting subject. So I don't know if there are questions from the audience for the speaker. I hope so.
So thank you for the presentation.
Thank you.
I would like to pick your brain on a problem we have in robotics about measuring performance and the standardization of the performance measure for robotics applications. So we typically work with different robot platforms in different laboratories, trying to develop different technologies. So these prevent us that we compare directly the performance of our system with respect to another system unless we have exactly the same robot. That is very rare, actually don't happen. So are there any kind of suggestions, insights, ideas you could have so that we could have like more, I don't know how to put it in words, like more concentrated advance by comparing actually the performance of the system we have. So how could we reach a standardized measure for robot platforms or the performance of the tasks they are doing if we have most of the time different settings? So that would be my question.
Okay, thank you. Your question is very, very, very interesting. something that people does not know, that measurements have two phases. The first fundamental phase is a political one. For example, unit of measurements. Why meter and not yard? It's a political convention. So the first way to reach a standardization is to meet people and to take decision, common shared decision from a political one. There are a lot of standards, especially, for example, in the IEEE, but there are standards also there are a research group in IMECO. There is a TC that is a TC for robotics. And I suggest you to see in these communities, to see what they are developing as standards. But before, there is I think that we are still in a phase of talking each other, and because it's difficult to reach a standard. A standard means that, first of all, we need to share a common vocabulary. For example, if you take the standard 1241, the standard 1588, I'm also the editor of a standard about the jitter, the measurement jitter. The first thing that you do is the vocabulary. We need to use the same word to express the same concept. Once we share the same vocabulary, then we say, okay, this measurement must be measured in this way, using these steps. Or often there is no one way to measure, but different ways according, for example, to the platforms. But according to the same platforms must be the same way to operate, and you have to declare which measurement methods you have used, which instruments that you have used, and so on, in order to guarantee repeatability and to guarantee that same numbers means the same things. Of course, in measurements, the word equal does not exist. There is the word compatibility. Compatibility means that the bound measurement value, the expected outcomes, the ones that is most probably plus or minus the uncertainty for you and your colleagues, have some common points. Intersection is not null. This means the two measurements are the same, although you are expressing different value from measurement and uncertainty. So I think that the first steps that must be done is from a political way, and I suggest to see both into the IEEE and in IMECO to see what they are doing now. Yes.
Is there a way that you foresee we can promote this from the scientific field?
Yes, sure. Yes, sure. For example, to promote these problems, I suggest, for example, to study the literature, of course, and to propose a review paper highlighting how different scientists, different research groups propose different measurement method and achieve results that may be the same, expressed in a different way, or give the same results, but after, for example, the problem of linearization. Okay, often when you know ADC, analog to digital converter, you have to express one of parameters that characterize the ADC is the integral non-linearity. Okay, it is just a parameters. It is standardized. It is a number. It is not a number really. It must be a curve. But seller give you a number. But what this number means is a chaos, because you can define different line, and according to this line you achieve different value. So an INL with a lower value can represent a bad ADC of another ADC with an INL with higher value, because you have changed the definition of the interpolation line of your results and you do not declare it.
First, a small fact, a link to the talks we had last year. You have shown in one of your first slides a wire with shape memory.
Yep.
Last year we had a very nice talk about pasta. Perfectly flat pasta, but once you put it in water, starts curling, twisting, taking...
Because it's passed from in a gel form.
Well, it looked like real pasta.
It's looked like real pasta, but it's the nitinol is, in my opinion, last application that they have done. Come si dice alettone? At the end of the cars, you see that there is, you can change the aerodynamic shape by using this nitinol wire. And also this wire can offer you some super elasticity. I mean, it's differently from the normal materials that you have an elastic phase, and then you have the curves that say, okay, now it's broken, and if you reach this curve, you cannot bring it as it was before. With nitinol, you have this shape that is the elastic phase, flat, then again elastic phase, and then the break phase. So it is something that people are studying in order to create different for example, muscle for robots. And if this muscle of robots can also include sensitive capacity, I think that we can open new scenarios also from a measurement point of view.
Okay. And then a small question. You have shown accuracy, precision. Okay. Now in medicine, we are used to work with sensitivity and specificity. And I was wondering whether, for example, in your application with cracks in a wall, it's not more, I would say, intuitive to say sensitivity and specificity rather than accuracy and precision.
This concerned with a different concept.
Sure.
So this is a dialogue problem. So we need to unify the vocabulary, give the right definition, and of course, accuracy and precision serves to define sensitivity and all the other medical terms and the medical evaluation. But it is typical for us. When we measure the fever, and we have 38.5 Celsius degree, and we take medicine, and the temperatures comes 38.4 Celsius degree, it was effective or not? Probably not, in our experience, because in our mind, we have this concept of uncertainty. And 38.4 and 35.0 is the same things because these are compatible measurements. So the medicine was effective or not? So we need to use, we need to standardize also the language in order to serve us. And the measurements can use these key roles to, is the common denominator for all different science, because each of us do measurements. For example, my experience as general chair of IEEE Metroliv-ENV, Metrology for Living Environment. Living environment is huge. And in living environment, we do a lot of measurements from chemical point of view, biological point of view, structural point of view, colorimetric point of view, light, so all the electricity, power consumption, and so on and so on. We have a lot of scientists from different background, but all of them use measurement to talk each other to create collaboration. So I hope that I have given a reply to your question.
Are there other questions?
The microphone is not working, so sorry. No, it's not working.
I will.
Can't hear anything, so
Okay, we can repeat the question.
Okay.
we can repeat the question. So just ask the question only.
Okay. So as you may know, I'm fond of full diagnosis, and so you different sensors. If you think about the monitoring of the structure, for instance, all these sensors can fail somehow, can be subject to faults. So I was wondering how you cope with that. If this is included in your work, or if there is need for extra work on that.
Okay, the question concerns about the fault of a sensor can have, and how to deal with this, right, Michel? Sorry to synthesize too much. And yes, it is a huge problem. It's a huge problem because, for sure, we cope with this with redundancy, with the knowledge of the model. Because before you do a measurement, you need to know what you are measuring. So you have a model, and you know also the dynamic of this model. Of course, the uncertainty on the knowledge of the model is directly reflected into the uncertainty that you achieve with the measurements. And if a sensor gives a value that is out of too much out of what you expect, probably the sensor does not work properly. Or you can use the redundancy. Instead to use one sensor, you can use two or more sensors. And also nearby sensor, for example, in the case, in the application of the detection of crack to one buildings. Because often we have noticed also from the history that if there are problems on the ground, this alarm must be shared among the nearby buildings. So we can use this information in order to cope with the
scenario where we need to use sensors. Would it be interesting to find compatible types of sensors but use different sensors together instead of one type or one thing?
Of course, use different. The question is how to use different sensors, and if it's yes, of course, we often do that. For example, into the EMU, you have different sensor, and you use information fusion in order to improve the accuracy. So this is typical. The problem is the cost, because measurement science, when you develop the uncertainty model, the uncertainty model is not just a formula to know which is the uncertainty, the final uncertainty on the measurement, but it gives you also an idea on how to improve the uncertainty containing the cost. Because you can always make a better measurement. But this means increase the cost. And to increase a few, to reduce a few the uncertainty, often you have to pay a lot. Consider that when you are buying something, depending on the complexity, the cost of the measurement increase. For example, to make an egg, when you buy an egg, the 10% of the cost of the egg is related to measurements. If you buy a Ferrari, almost 45–50% of the cost concerned with measurements. If you buy a jet, this percentage increase. Why? Because you need an increased accuracy. I mean, you need to reduce the uncertainty of the measurement. So it depends on the cost. Yes, it's a very good solution, also because some sensors, so some methodologies are robust to some magnitude of influence. Other sensors are robust to other magnitude of influence. So if you can use different measurements, different sensors, different measurement method to achieve the same measurement information, it's very good. It's something that we do, but always it depends on the cost.
Okay. And do they need to be compatible?
Of course, yes. They need to be compatible because it means that you are saying the same things. Note that the compatibility must be assessed also if you use the same measurement method, with using the same instruments. The compatibility is the first things that you need to assess. Welcome.
Okay, so I'll steal your microphone to
yes, sure.
to close this first part of our first meeting. So I would like to thank again the speaker. Very important thing that I want to reiterate, the Brussels Institute of Advanced Studies is not just a place where we give seminars and the thing ends there. Francesco will be with us for the next month or so. So if you have any question, any curiosity, or any idea of collaboration, He will be based in an office here in this department. Pass by, bother him. He's here to be bothered. So
I will never be bothered. Thank you. You're welcome. Always welcome.
So with this, I propose to take a pause so that we can get some coffee, and we will be back probably in 10-15 minutes. Okay. Thank you.
Thank you.
Right.
Yes.
All good. Okay, so good afternoon, everyone. Emanuele already introduced me, so I won't do it again. And so what I want to tell you about today is this work that I recently finalized in collaboration actually also with the Bristol Robotics Laboratory in the UK. And what we attempted to do in this work was to explore how robot swarms can be used for intralogistics purposes. Now, I will go a bit into the details of how we actually did this. This was mostly a proof of concept, so all the work that we did was actually in simulation. So if you expected to see some nice robots moving around, I'm sorry to disappoint. But in any case, I think the results that we obtained were rather interesting, and I'll be happy to share them with you. But also I want to give a hint of flavor of how I believe that such solutions could be implemented and the impact they could have in terms of sustainability, since this is the core idea of these seminars. So just to start with some context, what exactly is it what we mean when we talk about intralogistics? So, okay, I'm just going to let this hang here. Even though there is no fixed or official definition of intralogistics, generally we understand it as the management of and optimization of the flow of information and materials, maybe in a company, in a warehouse, in a distribution center, and so forth. Now, if you look at this thing at the right-hand side, this was collected by Eurostat and published by Eurostat, and it shows that in 2021, the transportation and storage sector actually accounted for about 17% of all fatal accidents at work in the EU, and about 9% of all non-fatal accidents in the European Union. And if you actually go deeper into the statistics, this is usually about all the fun things that happen when you handle heavy things, even with the utmost care, like sprains, dislocation, shock, concussions, and these things. So it's clear that the introduction of robotic systems into such environments could bring some benefits, be it through the aid of workers or altogether replacement for the handling of these heavy stuff like packages and pallets and so forth. Ooh. So how has actually robotics been introduced into these ideas, particularly more towards mobile robotics I will talk about. So far I will give like 3 quick examples. One of them you probably know already, the one here on the left-hand side. This is what the robots that Amazon uses for the distribution centers. They acquired these orange mobile robots from what was back then known as Kiva Systems, and now I think it's Amazon Robotics, something like that. And these, I wouldn't call them little guys because they're actually pretty big, but they move along some grid lines on the warehouse, and then they can lift these specifically designed shelves and with some platform and move them around along these grid lines to move them around the warehouse. This is very practical. This second example is a shot of the Hive. This was developed by Ocado System. It's a distributor in the UK. And this essentially consists of an array of vertical shafts. And these robots here move along rails on top of these shafts, and they can pick items from one place and move very rapidly to another and drop them over there. And they operate on a centralized entity that distributes all these tasks to individual robots. And finally, we have a crane, very large crane that can be used for weighing and moving of pallets and packages around the warehouse. So what you'll notice in all these 3 cases is that, in general, these systems require some rather specialized infrastructures. In the case of the Hive, this is very obvious that you need an entire system developed exclusively for this. But even in the case of the Amazon warehouse robots, you need the specific shelves, you need the lines, you need the space. So they're not really suitable for, let's say, off-the-shelf solutions. And additionally, now, I can't confirm this because this is rather private information, but they look pretty expensive to me. So I'm going to assume that they're pretty expensive and not really affordable by the most economically challenged communities. So how does swarm robotics come into play? Now, before I talk about how it comes into play, I want to give a quick overview of what swarms are, because robot swarms is an often misunderstood concept and often taken for common or general multi-robot systems. But what we talk about when we say swarms is a collection of relatively simple robots. But relatively simple means with respect to the task at hand. They operate in large numbers. So here we're talking about from 5 or 10 to 1,000 or several thousands in principle. In practice, 1,024, I think, is the biggest there has been. Then these robots coordinate in a distributed manner, so there's no central control entity, and they interact with one another and their environments locally. Now, what this allows us to build is systems that are, in principle, highly scalable, so you can add or remove robots without truly compromising their performance. They're fault tolerant, so they can afford to lose some of the members, and they're flexible in the sense that they are supposed to be able to adapt to changing environments or to different conditions. Now, these properties are all very nice to have in a robotic system, but in order to introduce them in intralogistics, we wanted to go a bit further. So how do we actually take these properties and put them to good use in intralogistics? Now, one thing to keep in mind is that because these robots are relatively simple and they operate in a distributed manner, these robots are designed so that they are easily replaceable. So that if some element in your swarm breaks, you can just take it out, put a new one, and the performance should not be compromised. So in order to apply this to intralogistics, we looked at what is known as collective transport. Now, this is something that is often seen in nature, particularly one good example is of ants. When they find a thing that is too large to move around by a single ant, they collect, they recruit other ants, and all them together, they move things from point A to point B. Now, how do we do this with swarms? So for this, some guys at the Bristol Robotics Laboratory in the UK cooperated with Toshiba, and they came up with this neat little platform. It's the DOTS robot. It's about yay big. And it weighs 3 kilograms. Costs not even £1,000, which is about, say, 1,100, 1,200 euros, which is pretty neat. And it has a bunch of sensors. It has holonomic drive, but it also has proximity sensors, cameras facing horizontally, it has GPUs, CPUs, a camera pointing upwards, and a lifting platform that it can use to carry payloads of up to 2 kilograms. So the idea behind this platform was that group of these DOTS robots will be able to move underneath the platform and then all together coordinate to lift it and then move it to a desired location, much like ants do. With this little, like in this little diagram, sort of. And so what we thought is, how can we actually put this into practice? And how can they develop a system that actually does that? And that is when we get into what we actually did, which is all operate in this simulated world. Now we consider a very simple scenario. Let's say you have an environment that is 5 meters by 5 meters, and you have a wall that's covered with some fiducial markers, like Aruka markers, that can be detected, and then the robot can measure the distance to it and basically its relative location. The idea was to have a swarm of robots that can carry these neat little items towards the nest in a collective manner. Now these items, as you can see, have two more, let's say, fiducial markers in this case that can be detected as the robots travel underneath them, and they would give the robot some information, like a unique ID of the platform and the number of porters that are required to carry them, in this case 2. So these platforms have designed such that 2 robots are required to move them and a single robot cannot actually move it. The goal then is to distribute some of these robots, which we made as a simplified version of the DOTS. So it has holonomic motion, it can attach or detach himself from the platform, so from the items using the platform. It also has some fiducial markers around them as well, so that other robots can see them and identify them. And then they have some sensors, like distance sensors, cameras for detection of the markers, wireless communication, and they also have a compass, and they operate in a synchronous manner. Now, this is usually a big concession in swim robotics, since we assume that the robots operate in a distributed manner without access to a common clock. But as a previous speaker already mentioned, the synchronization of clocks is a rather challenging problem on its own, and so here we kind of put it aside and focused on the thing that we wanted to show. So, how then did we go on and control this swarm? Now, notice that when I talk about control of a swarm, what I actually mean is, how do we control the individual robots such that the swarm does what we want it to do? That is the main problem in swarms, which is not very easy. And here I'll talk about more of a high-level control than the low-level control that you're probably used to seeing around this lab. So the first stage of this controller was a behavior tree. Now, what is a behavior tree? Behavior tree, like this thing right here, is an acyclic graph, directed graph, that's composed of nodes and edges. And the way a behavior tree works is, upon each control iteration, a signal starts from the root node and then is propagated down the branches according to the rules that define the nodes here. So these nodes might tell you that the children will be executed in a sequence, or that there will be one of them selected and that one will be executed. Or you can have a node that is a conditional node, and so the child will only be, this is a horrible thing to say, but the child will only be executed if the condition is true, and so forth. Now, when the signal reaches the leaf nodes, these leaf nodes can interact with what's known as the blackboard. It's a list of key value pairs that contain information, in the case of our robots, about the environment, about what they sense. So in this case, our robots provide information about, let's say, mean position of nearby obstacles or nearby robots, the position of the nest, if perceived within its local environment. And so these leaf nodes can read from the blackboard and can write to some entry of the blackboard. And eventually each robot will execute this behavior tree and will produce what's known as a vote. This vote is a desired velocity and a desired actuation of the platform. So this is the first stage. Now, once each robot has produced a vote, a desired velocity, and a desired platform actuation, it will go on to the negotiation stage. Now, I'm not going to go into the details of this. I'll just do more of a high-level overview of what's happening here. So each behavior tree produces a vote, a local vote. What this means is that the velocity, for instance, is given its own local frame of reference. Now, what each robot does then is it rotates it to a common frame, which can be obtained through the compass. And then it appends some more information to this vote, like an identifiers and so forth. More importantly, what it appends is a group identifier. Now, this group identifier will have the value of the item under which the robot is placed when all the lifting points of the item have been covered. So essentially what this allows is that the robots within or carrying one single item will be able to coordinate with one another whilst ignoring all the other robots in the environment. And this is very useful because then the robots, what they can do is synchronize in order to carry multiple items simultaneously towards the nest without interfering with one another. So then what they do is every robot will gather all the incoming messages from their neighbors, and then they will achieve some, so they will do some averaging, and then they will decide whether to move towards a common location or to actuate the platform to lift or place the item. Finally, since this is done in the global frame reference, they rotate it back to the local frame and they move. In global terms, it's quite straightforward, but the variables look extremely ugly. So what this means is, to give a more pictorial representation, suppose you have two items that are right here, and each of them has two lifting points. Initially, there are no groups. As robots start covering the lifting points of the items, they start forming groups, and then the negotiation strategy kicks in, and these robots coordinate with one another, these robots coordinate with one another, but overall, the groups don't coordinate with each other. And this is what allows for the simultaneous transport. Now, obviously what I haven't told you yet is how do we actually construct the behavior trees. So what are the nodes that compose the tree that allows the robots to move around or to lift the platform and so forth? So what is actually the control that's happening here, and how do we evolve it? Sorry, I kind of spoiled it there by saying evolve. So as I mentioned earlier, when we talk about designing control for swarms, we talk about designing controllers for the individual robots such that the collective exhibits certain behavior. Now, this is very challenging, and in swarms we call this the micro-macro problem, because it's very difficult to predict what the global behavior will be when all you have is a lot of local interactions. So one way to avoid the arduous process that is manual design, which is you start with a controller, you test it, you see that it doesn't work, you refine it, and then you do this a lot, is to go into notions of automatic design. Essentially, you cast your design problem into an optimization problem, where essentially you explore a space of possible solutions and you evaluate which one is best at completing the task at hand. So what we did was apply or implement what's known as genetic programming. So for this, I won't go into many details, but I'll give you a brief overview of what happens. So you start with a random population, in this case of behavior trees. So you initialize some random behavior trees, and then you apply these three operations, which are called reproduction, mutation, and crossover, which are essentially replicas of what happens in asexual reproduction. And through these operations, you generate a new pool of candidates. Now, this new pool of candidates you evaluate at the task at hand, at the one of collective transport, and then, depending on their performance, you select a bunch of these candidates, and they form the new generation. And then you repeat this process a bunch of times. In our case, it was 400 times. And eventually have some candidate solutions out of which you can select the best one, most likely. So in this case, the fitness was this little function over here. And what it represents, essentially, it's this function will be 1 if all the items are constantly moving towards the nest at the maximum speed, which is clearly unfeasible, but it gives a nice theoretical upper limit to what we might expect. And it will be 0 when no items move. So essentially what we're trying to maximize is the idea that the items are constantly moving towards the desired location, which is good. And now the final ingredient here is what are the actual nodes, what are the actual modules that compose the behavior tree. And for this, we borrowed an idea from what's known as automatic modular design. I won't go into the details of automatic modular design, but the basic idea is that we define some low-level behaviors, which we then combine into a certain architecture. It could be a probabilistic finite state machine originally, but it could also be a behavior tree, which is what we've done. So what we did was to define some low-level behaviors, like exploration, which is that the robot executes some ballistic motion around the environment, so move in a straight line, and if you run into an obstacle, turn and move in a straight line again. They can also stop, they can be attracted or repelled from nearby robots, they can go towards or away from robots that are under a lifting point but still need more porters to carry an item, and then they can activate the platform by picking or placing an item. And we also find some conditional nodes that will return true depending on the number of neighbors, number of recruiters, if the robot is a porter, if it's at the nest or is carrying an item, or with some fixed probability. Now the idea is that all these behaviors and all these conditions have certain parameters, and so what the genetic programming algorithm does is essentially assemble these modules into behavior trees and then apply the genetic programming operations that I mentioned earlier. And so, I've given a lot of details of what we did, but what actually came out of all this? So we run 10 iterations, 10 independent evolutions of our behavior trees, and we obtain something like this. So essentially, what you see is that without going into the means or the medians, we have one solution that achieved a performance at the end of the 400 runs of 16%, which, all things considered, is actually a lot better than we expected originally. And it was this little guy over here that achieved this. And one of the advantages of behavior trees that I didn't mention is that they are rather readable. So if you know how the nodes, the structural nodes work, then identifying what the robot is supposed to do at every moment in time is actually very straightforward. but I won't go into this right now. The point is that one other thing that you can do is to follow some mechanical procedures to then prune these trees. So you can determine that some nodes, like the ones over here, will never be actually ticked, and you can remove them. And essentially what you realize then is that you have two main subtrees. And when you apply this and you take this behavior tree, give it to all the robots, so each robot has its own copy of the behavior tree, and you run it, this is what happens. Hopefully everyone can see it. So essentially what they do is, first of all, they try to pick an item, but when no item has been found, what happens is that they just keep moving in a straight line until eventually they might find the lifting point. Once they do, they try to pick the item, but since they might not have enough porters, what they do is they just wait until enough porters have been recruited, and then they will try to place the item. So they will move towards the nest and drop the item at the nest. Essentially what this does, or what this behavior tree achieves, is that the robots can explore the environment, they can locate the items without any global information, without any previous knowledge about what the items were in the first place, and then they can form the groups under the lifting points and simultaneously carry multiple items towards the nest while also avoiding obstacles in their path, which at the moment when we did this was rather novel and rather neat. And so this is what I wanted to tell you guys about. Just to draw some final remarks, essentially what we're looking for is to implement a decentralized negotiation strategy that was based on direct communication and would allow a swarm of robots to simultaneously carry multiple items, multiple heavy items, towards a desired location. We did this by implementing some genetic programming, and that actually gave us a rather human-readable controller, which is very nice if you want to know what your robots are actually doing. And the benefit that I see of such systems is that due to the affordability, they can actually be used by more Chinese communities, and they provide a utility as an, let's say, out-of-the-box solution. Thank you very much. If you have any questions, I'll be happy to answer them. Nailed it. Does it work?
The questions I see there, so I'm giving you the microphone. It seems now it's working again.
Not you?
Is it working?
Is it now working? Let's see.
Which way for the delay?
We have to wait for the delay. No.
Pose the question, yeah.
I'll just repeat, yeah. If I understand it.
Well, they did hear you, actually. They said that they did hear you.
It's just very, very quiet.
Okay, so
Just keep it very close to your mouth.
Okay, so if I understood correctly, the communication between the robots is only when they're grouped up and not beforehand?
No, so as in yes, but no, the coordination is only between the group, but the communication actually happens all the time. So each robot is broadcasting the message that it has constructed with its own sense information, and it's only upon reception of messages that contain the same group identifier as their own that they use that information to coordinate. But every robot is constantly broadcasting and constantly receiving messages from the robots in their neighborhood. So the communication is always happening. It's only knowing when to use that message for coordination that plays a part.
Because it looked like in the simulation, it looked like they didn't really, when they found an item to carry, they didn't kind of like call out to have someone to come help.
Indeed, and that's because the controller actually never used the recruitment behavior that we had provided as a possibility. So let me see. Here we did define some, recruitment and anti-recruitment behaviors. So we made it possible for the controller to use these behaviors. So essentially they will, in a way, a robot could sense if one of their neighbors was actually waiting for the porters and then move towards them in order to find the item. But then the genetic programming algorithm decided that this behavior was not necessary to produce control software that actually worked at the task at hand. So we were not really forcing them to use this. We simply provided it because we thought it would be good candidate solution that some controller might find use for it. And
did you do like a test to counter proof or like I don't know, use another behavior tree within recruitment? Because it seems like the first thing that comes to mind.
It seems like it. So I did not particularly do any manual tuning afterwards to see what would happen if I swapped behaviors. So kind of the whole purpose of the automatic procedure is to avoid this, because so what happens often with swarms is that you might think, so you think intuitively this should work, but then you try it, and the problem is that in a swarm the robots experience a lot of interactions that are very unpredictable. So you move and then you run into another robot, that one reacts in a noisy, unpredictable manner, and then it runs into something that it shouldn't have. So this all blows up rather quickly. So even if you think that applying a certain modification will work, is not necessarily the case. And yeah, I was actually a bit disappointed when I saw that the solution didn't use any of these fancy things that I had given it, but it is what it is.
Thanks. Nice. And maybe another question, a bit off topic, as you used the ants as an example. Is there any research, or have you ever thought about, like, you talked about the recognition of the robots underneath themselves, of any chemicals in terms of like recognition, other than visual or technical?
So the use of chemicals or like pheromones in the use of pheromones in robot swarms is a thing of its own. In fact, that guy over there has been working with this, and it's a rather challenging thing by itself. Essentially because you don't really have the actuation and the actuators and the sensors that you would need to replicate exactly the same way that chemical pheromones work is not really available. Like, they don't exist. So essentially you need to try to devise different systems that somehow replicate this kind of behavior, and this usually by itself requires additional infrastructure. You need to prepare your environment, so it's not actually as easy. And there are other ways that you can try to do this by having messages that so through direct communication, messages that sort of decay over time, but it's not really as straightforward as one might think, unfortunately.
Yeah. Okay. Thanks.
No worries.
There is a question from the chat, so Andres is reading for it.
Okay.
Right. So we have a question from, excuse me if I butcher your family name, Hugh. Well, they loved your presentation, so congrats.
Well, thank you very much.
They say that they are just starting with swarm robotics, and they ask what would be the main issue that they need to look for. I imagine they look for, like, what's the big
the main issue in swarm robotics,
diving in,
or in so what to dive in
they are just diving
into swarm robotics.
Yeah, so probably what do you recommend someone new to the topic?
Wow, yeah, that's a tough one. So so what I'm working on right now, that's what interests me the most, and I think is perhaps one of the largest open questions right now is modeling of swarms. Essentially, swarms are they're difficult. They're rather easier to model when you get to infinitely large systems, because then you can make some approximations that work okay when you get into simulated environments. But then once you get into the sizes with which we expect to operate, once you get to the tens, the hundreds, or even the thousands of robots, these models break down. And so I would say, like, perhaps the highest pressing, or one of the highest pressing matters right now is how to model, how to ensure that you have a mathematical model that tells you what your swarm is supposed to do at the collective level. Now, I'm not entirely sure if this is the place to start for a beginner, since this is an extremely difficult matter. But if you were to dive into robot swarms,
Is that one of the other fellows asking, or? Yes, it's one of the other fellows asking. Maybe you should just have a chat. And then
actually, that would be fantastic, is it?
to Brussels.
Yeah,
Okay,
they said that they will think again about swarm robotics and that they will see you in Brussels.
I'll be here, yeah, for sure. That was a good question. I kind of want to think about it now.
Other questions?
I have a question, if I may.
Yep.
Okay. Okay, maybe you get this question all the time, but looking at the simulation and all the robots moving and stuff, I wondered, are there, probably not in your work, but are there any methods to detect and probably hinder malicious agents? If I was like an evil person and I wanted to really stop you from delivering a package, I would sneak in my evil robot.
Yes, actually. So part of the other researchers in RIDIA, so the group of Marco Dorigo, they are working on robustness to Byzantine robots. So yeah, they call them Byzantine robots. So essentially, robots that do not work the way you would expect them to. Now, we've had many discussions about whether this is exactly the right word they should be using for it, because sometimes they are malicious by intent, but sometimes they're just faulty. But is there really any difference when it comes to the effect they have on the system? But that's a different topic. And the point is, yes, there is actually ongoing research on how to tackle these systems. And the way they do this is through the use of blockchain technologies. Don't ask me many details because I will not be able to answer them. But yeah, there's a lot of work going on about these things. Apart from blockchain uses, I'm sure there are other cases, but I can't really think of them right now because Huh?
Your group is to work on neural group where they exchange information by being a part of the group.
Yeah. For example, yeah, a robot needs to be a part of the group to, yeah, in a way, there's a little fault tolerance here. Why not? But it wasn't really targeted towards that, but I guess it could work.
Francesco?
Congratulations for your nice presentations.
Thank you.
It's nice to see that evolution of consensus also for in these topics. Nice. Questions. There is a maximum number of cooperative robots to move something. I mean, you need to foresee the fiduciary points under the platforms, for example, or it's in the future you can requires how many robots you need.
So in this particular implementation, since this was more of a proof of concept, we went for the very basic scenario. So in fact, the case I presented here is with or items that have only 2 lifting points. So it's basically the minimum valuable product, if you want. But the way it was designed is that it would be able to carry any items so long as all the robots were forming a fully connected network topology. And essentially this allowed for the interaction to occur within one iteration of the controller. Now, one of the issues with swarms, one of the main and most annoying issues of swarms, is that they interact locally. So what this means is that if 2 robots are too far away, they will not be able to perceive each other, they will not be able to interact with one another unless they do some kind of hop-based communication or things like that, or they do some kind of, I forgot the word. They interact indirectly through the environment. Stickmergy. Stickmergy is the word I was looking for. So in this case, we specified the number of robots that had to be available on booth in order to carry an item. But in principle, I can't really see a reason why you wouldn't be able to have more or fewer, so long as they're able to actually carry the item. It was more based on, okay, if we have an item that has this weight, how many robots will we need? Just divide it and put it over there. Well, I mean, in this particular case, other than the robots themselves, all that you need is to maybe put some fiducial markers under the platforms so that they can carry them. Obviously, I did not manage to implement a solution with zero infrastructure, but all things considered, I would say that sticking a fiducial marker or some fiducial markers under a platform is sort of okay. Now, could this be improved in the future? Of course. And I'm sure that the people at the Bristol Robotics Laboratory who still work with these robots are working on this as we speak. But as a first approach, I think this was a rather neat in diminishing the amount of infrastructure required. I'm good. Yeah.
Okay. The microphone again is.
So I have actually two small questions. I might start with maybe one which is more broad to answer. So in the simulations we see that you went to the minimum type of swarm communication with two robots. We see that in order to model these things that they're based on your tree or the tree diagram and basic mathematics. I was just wondering if adding more and more robots in order to communicate between them just in groups in order to lift a certain payload. By keeping the same model, we should be able to add robots without being a problem, I guess. Is there still like a limit due to maybe computational or just communications between many robots just to lift one thing? Or you think that it might be able to just be robust enough to add maybe 50 robots together that need to lift one payload, the same model would still be okay?
I think if you added 50 robots, the problem you would first run into is the locality. So now, depending on the range of communication, of course, you can increase it and then remove all the problem of locality and just have a multi-robot system. But assuming that all robots interact locally, then the more robots you add, the more difficult it is to keep them all within range of one another. So in principle, I would say that's the biggest challenge to scalability of the items. However, in terms of the size of the messages, let's say, when we design these messages, we try to keep it as compact as possible. So I can't really foresee there would be any kind of buffering or memory issues here. I think you would first run into the locality problem, and then you would run into the messaging or memory problem. I think, then again, this was all in simulation, and so the messaging part is, simulated.
And then I this is more just basic curiosity, but seeing what you're doing, so getting a package to the nest, in the simulation they disappear, but of course in reality they don't disappear. I was just wondering if they know exactly where to put it, or if they feel that they should go, for example, to the nest, and that there is an obstacle, do they, in the way it's coded, I guess, do they automatically try to put it next to it, or do they keep barging in, or do they actually know where some packages are already positioned in order to know to not go to that position, to another one?
So yeah, in principle, so actually, you mean avoiding previously placed items? So now the actual design of the items in this case was extremely simplified. So we did not actually implement let's say the legs, which might have hindered the motion of the robots. Now in principle, this should be avoided using obstacle avoidance algorithms. In this case, we figured it wouldn't really provide much more additional information. But in principle, yes. So as you saw in the video, which is somewhere, I don't know why I'm putting there. I'm assuming it's not liking it. So the robots are overall they are avoiding obstacles. So even while they're carrying an item, they are. You'll see in a minute. Even while they're carrying an item, the groups are avoiding obstacles on the way. So there's as you see over there. So there's no reason why they shouldn't be able to avoid obstacles that are at the nest. Now the whole point is that they're going in that direction, and the reason why they disappear is because they actually execute the place maneuver and they actually deposit them over there. However, in order to keep the simulations running as long as we needed to, we essentially took the item, once it was placed, we replaced it at the original position so that they could take it again and bring it towards the nest. And so they could, in principle, go on indefinitely.
And so in principle, if you need to apply this to a real scenario, you would just rely on collision avoidance in order for them to place correctly back.
Yeah, yeah. In this simple scenario, yes. I'm assuming if you have all the constraints, you would want to consider them in the design process. Yeah.
So I think we went quite a bit over time. So even if I know that there are other questions and I would have more, I would stop the formal part of our meeting here. I would like to thank again the speaker. And I would also like to mention that, as said, the presentation is only a part of our activity, and that you are absolutely not invited to leave the room, but actually, if you want to stay and have discussions with the people present, you are more than welcome. There is still coffee, and we will see each other also for the people online that could not attend yet next week at the same hour in a different place, because it will be the Experience Center at VUB. And with this, thank you again to everybody, and let's have our coffee. And thanks also for all the fellows and the other people that have been online with us. Thank you.